Good afternoon, everyone. And today's topic is about this one, longitudinal data analysis with clustered data, part 2. And I'm going to do some recap of part 1. And this is a topic we covered up to now. And objective of today's session is to review longitudinal data analysis with clustered data. So in the previous session, we reviewed how to incorporate correlated data. And today, we are going to review how to examine association between an outcome and a predictor after incorporating correlated data, or after incorporating correlated structure of the data. And well, today's data set is the same as previously, but I added GDP in the analysis in the data set. By the way, this data set comes from survey data from Chile. But this data set was modified to increase the data confidentiality, etc. So it's not real. So do not use this data set for your analysis. But this is to learn how to analyze. And the sample size is 446 year-specific cities. So we have 20 cities in this data set for 10 years for 2 sexes, for men and women. And today's study aim is as these two, there are 2 aims for today. One, if the baseline GDP per capita is associated with the rate of mortality change. And the second one is if the change in GDP per capita is associated with the rate of mortality change. So before we go on, let's recap of the previous session. And some of you might not be there, or it has been a month, so you might forget. We have 3 levels with 2 nesting structure. So in Chile, within Chile, when we do multiple analysis, we have other countries as well. But in our case, we have 3 levels. So within Chile, we have 20 cities. And within one city, we have data of several years. So they are clustered, meaning the data under city 1, they're kind of similar. So we have to consider this clustering effect in our data analysis. Also, cities within Chile, they are similar, but at this time, we don't have to worry too much about this clustering because we don't have data of other countries. And what we did as follows, first of all, we did a spaghetti plot to see the time trend, to see mortality changes by year in each city, to see how to have an overview. Well, the problem is, we can see general trend, but somehow it's difficult to know what's happening in the city in the middle, since the lines overlap. So we separate this graph by city. It's a bit small, and this graph represents one city for men and women. And by looking at this, I think we could assume that there is a linear trend across time and across cities. But they have different trajectories. In some cities, they are going up, and some cities we see decline as well. And then this one, we fit the line, and we superimposed or fitted the line. So by looking at, it's very obvious that at initial year, each city have different mortality ranging from here around 4 up to 8 well, women is somehow lower as compared to men. And the trajectory, some cities moving up, some cities moving down. So this implies that better to use random intercept as well as random slope to capture these city-specific trends for men and women. And when we moved to the regression model, we thought about these two models, one with Poisson and the other negative binomial. And in terms of equations, they are very similar. Well, what the difference is only here you see some star here, but here you don't. And what does it mean? The interpretation of coefficient, they're the same. Only how we model this is different. And we use robust variance estimators to account for any misspecification of the variance component, and especially for Poisson model, since we usually expect over dispersion, and by applying robust variance estimators, this part will be incorporated. And afterwards, we talk about what is the difference between these two. Maybe this part I don't go into too much. And then it seems that, well, when we look at the goodness of fit to the data, it might be better to use Poisson model instead of negative binomial. And this was a conclusion we had previously. And we are going back to today's main topic. And I wonder if you have any question up to now. No? Okay, now let's go to the next one. So again, this is a recap of what about today's aim. So there are two. One, well, I don't think I'm going to repeat reading this again, but there are two study aims we are going to assess using regression model. And so how to do? Well, we are going to use Poisson model. And if you're interested in, of course, we can do negative binomial model and compare. But for today's session, we are going to use Poisson model, multi-level Poisson mixed effects model with robust variance estimation with random slope. Here you see city-specific intercept, so random intercept as well as random slopes. Here you see subscript I, which means that the time trend differs by city. And now we are going to add GDP per capita because this is an exposure or predictor of our interest. And we are going to include this one in the model after accounting for within city correlation by including random intercept and random slope. Well, this one says slope, but well, there's a typing error, it should be slope. And using this equation for M1, so we include GDP at time zero, I0 meaning GDP of city I at time zero, meaning as a baseline, meaning for GDP as of 2005, we have data from 2005 up to 2015. And here we include also interaction term between this initial value of GDP and time. By doing this, we want to know, well, so this model tells us the effect of time varies by the value, by the level of GDP, okay? Do you have any question about this? No? So let's go on. Then the next problem is as follows. Well, here this is the equation we are going to model. And here we have interaction term, GDP and time. And the problem is both of them, they are continuous variable. Time is continuous and GDP is continuous. The problem is that, well, interpretation of interaction term between two continuous variables is hard, first of all. And secondly, this type of interaction, two continuous variables interacting each other. It's not observed very, it's observed, but they are not in this form, multiplying two variables. So this is what I mean by not often. We do see interaction very commonly, or almost 100%, or if it is not 100%, close to 100%. Always we see interaction, but in many cases we don't have power to detect interaction. But the problem is we don't see this type of interaction, continuous times continuous variable. This is what I meant by often. So what to do? The solution is we categorize one variable. So in this case, we are going to categorize GDP. And we're going to dichotomize GDP instead of using GDP as continuous variable. And in general, dichotomizing continuous variable is not a good idea. Well, in other words, better to use more than three categories, more than two categories, three categories or more. But here we are going to use only two categories because we have only 20 cities in this data set. And to divide 20 cities into three groups, it doesn't make sense. So here we are going to separate 20 cities into two groups by GDP threshold cutoff point. And well, we are going, before we fit the regression model, we are going to assess the association visually. And this one shows association between mortality rate on vertical axis on log scale, and GDP per capita without any transformation. And what is a problem you see here? Well, the thing is that this city has high GDP per capita as compared to other cities. So when we fit a line for this one, change the regression line actually. So if this point is high, maybe the regression line goes up. And if this point is very low here, this regression line may go down since this point is far away from this group. So what shall we do? Well, and also, before we go on to what shall we do, here we see blank. So we don't know what's happening. Well, we are going to talk about the association between GDP and mortality, but here we can tell a lot because we don't have data. Then we do this way. So I just plot GDP on the log scale. By doing this, so the distance from this point and this cluster of cities, they become, I should say, much closer. So, the influence of these previously outliers become less. At the same time, we have smaller space between this cloud and this point. So by observing this, we decide to use GDP after log transformation instead of using GDP as it is. And now, what is the association between mortality and time trend? And we want to know if GDP per capita in 2005 has influence in change in mortality rate. So I use a red color for the cities that had GDP per capita less than 15,000. I use blue color for the city with GDP per capita more than 15,000 in 2005. And these are the trend for men and women. We do see some slight change here, slight difference between well, these two category of cities, but it's not that big. At the same time, the time trend, they are parallel. The slopes are not different. So before we fit the regression model, we are kind of know that it doesn't seem that the trend varied by GDP in 2005, according to this graph. And now, go ahead.
How did you dichotomize the GDP?
GDP, I looked at the distribution of GDP and then afterwards I decided, and also I didn't want to use a cutoff of like 12.4, something like that. So I chose somehow rounded number. And also so that the number of city below and above the threshold become somehow similar. This is how I decide. So the meaning of well, there is no special meaning of 15 itself.
Okay, thank you.
Yeah, you're welcome. Then we run the regression analysis, and this is a model I use. Although here I use this one, but the GDP or this GDP, I log transformed. This is what I want. Forget about what I said. So these are dichotomized GDP, not a continuous variable. Be careful. Although I wrote it this way. And we are interested in this one, beta 2, or the coefficient for this interaction term, because we want to know if initial GDP affects the slope, or how the mortality trend differs by initial GDP as of 2005. And well, this is a result, and there are 220 records. This is what we expected for men and for women. And there are 20 cities, and each city contains 11 data points, because we have yearly data starting from 2005 up to 2015. So we have 11 data points for each city. So we confirm that we are using the right data, and then we jump into the coefficient for interaction term. Well, coefficient is this, and then p-value or 0.2 for men and 0.9 for women. So it means that we confirm that there is no change in slope which we saw in this graph. And just for the practice, let's interpret some of the coefficient. Let's look at the coefficient for t. By the way, this one, t, was calculated in this way. T equal year minus 2005 divided by 10. So that t, when we look at t, the unit of t is 10 years. And when t equals 0 means the year of 2005. So when we interpret this t, it's going to be like this. So there was a 3.7% increase in mortality in 10 years in the reference group, which is cities with GDP per capita less than 15,000. And then let's interpret this one. This coefficient or not coefficient, exponentiated coefficient for interaction term. So this means that the increase in mortality in the comparison group means GDP more than 15,000, is 3% higher or 2.8% higher than the reference group. However, this difference was not significant. This is how we interpret coefficient for interaction term. And do you have any question before we move on?
I have one, Goro.
Serena.
Always when you include some exposure, you have to include the interaction term, no? Just to show that that's GDP at the baseline. Or not necessary to include the interaction term.
Not necessarily.
No.
Because at this time we were interested in if the initial GDP affects the change of mortality trend. For this reason, we are checking interaction term. But if you are not interested in interaction between two variables, you don't have to. Or
Okay.
Maybe better not to include sometimes, because because by including interaction terms, interpretation of coefficient become always difficult. Well, here we can see in the reference group, so we cannot read the coefficient in a simple manner. In this sense, if we don't think that there is interaction, it's better not to include.
Okay.
But sometimes it's added value. It has added value when data doesn't fit when the model doesn't fit the data well. One option is to include interaction term as well.
Okay. Thank you.
You're welcome. Any other questions?
Yes, to clarify, finally you use the GDP dichotomized,
Yeah.
but you did the graph with the log of the GDP just to show the trends, no, and the relationship with the mortality rate. But in the model is the dichotomized GDP that did you use?
You're right. You're right, because so log transformation is not necessary in this case.
Okay.
Because we just split into two.
Thanks.
Okay, so let's go to the next one. So we go to the aim 2. We are interested in looking at the association between change in GDP and change in mortality. So previously we are looking at the initial value of GDP, but now we are interested in association between the change in GDP and change in mortality. How to do so? Well, still we are going to use this model as a base, and afterwards we are going to include GDP per capita. But this time, we are going to split GDP into two components. One is cross-sectional and the other is longitudinal. Or sometimes we call cross-sectional as, in this case, between city association, and longitudinal. So it means that within city association. So within city meaning within city by time or within city how change in GDP affected change in mortality in each city. This is what we want to know on average. And there are two ways of decomposing or partitioning GDP. First one, well, for GDP IT means GDP of city I at time t. This is the meaning of this subscript. And this can be rewritten in this way. GDP IT, this is the same as this one. But here I added city-specific GDP or city-specific mean of GDP. This is the meaning of it. Bar mean average, and I is mean city I. And because we took average, there is no time component, and that is the reason why you see dot here. And so I added this quantity, and also I subtracted this quantity. So when you do this math, well, this one and this one cancel out, and which is the same as this one, GDP IT. Okay, and then here I just reordered these three terms. So the first one you see city-specific mean of GDP or average GDP across years, plus or GDP minus mean GDP. So this is a difference of each year of GDP as compared to each city's average. Okay, and this is a this is one way how we can decompose or partition GDP into two components. And this one is used to assess cross-sectional effect. And this one, the second term, is going to be used to describe longitudinal effect. And another way is as follows. We do the same type of partitioning, but here, instead of using mean GDP, city-specific mean GDP, we use initial value of GDP. And we do the same thing here, but here we have initial value of GDP and the difference between GDP at time t as compared to initial value. So if there are two ways, which shall we use? This is the next question. And the answer is it depends. Okay, this is a equation. So in this equation, we added two terms, this term and this term, cross-sectional and longitudinal components. So the next question is then, as I said, well, which one shall we? Go ahead.
The mean of the GDP by city is the mean during the period?
Yeah, during the period.
Okay.
Between 2005 to 2015. So the first model meaning, well, decomposing using mean GDP has an advantage that model can adjust for time invariant. Time invariant meaning, well, the value doesn't change by time. Time variant cluster level covariates, whether observed or not. So meaning, well, we may not have some data, but we can, using this model, we can adjust not only for observed, which we include in the model, but also we can adjust for unobserved covariate if they are time invariant and cluster level. Okay, so this is a good advantage. And the second option, well, this one, well, this is a initial value of GDP, and this is a change starting from the initial value. So it's easy to explain. So this is one thing we may consider. So easy to explain. And also, this model can give us unbiased, well, less unbiased estimation when data are missing. What does it mean that? Well, when we do longitudinal studies, well, here, different from our studies, like we have cohort of several people, and we want to know, we are implementing longitudinal study, and always people drop off from the study, right? We cannot follow up the same individual in 100%. And when we have this type of data, sometimes this model is better as compared to the first one. So there are pros and cons. And so what shall we do? And the answer is it depends. But in general, Saruba prefers the first option. First option meaning this one, use a mean value instead of initial value. And how about in our case? Well, it's kind of tricky. Aim one, we look at the association, or we look at using, well, we did analysis using GDP in 2005, which is the initial year. So when we want to compare the result between aim one and aim two, maybe we should go on and use this model, the second one, because we are referring to the same time point. But at the same time, we don't have missing data because we have data of 20 cities continuously from 2005 up to 2015. So in this sense, we can go to the first one because we can control for these unmeasured covariates, which can be confounded. So what shall we do? Well, in my presentation, I did analysis using two methods to see if there are any difference. So before we go on to the regression model, this is exploratory data analysis. The left figure to see the association between mortality and GDP cross-sectionally. This is as of 2015, which is the same as previous one. So there is some declining trend as GDP per capita increases, or the city that have, well, cities with more GDP tend to have less mortality rate in general. Okay. This is what we see cross-sectionally. And this graph is a little bit complicated. And the horizontal axis, I took the difference in logged GDP, but using the initial GDP. So, well, I use this notation, but more correctly, I should say logged GDP of time of city I at time t minus logged GDP of city I at time 0. This is what I should say. And for the mortality vertical axis, same thing. I calculated the logged mortality in time t minus logged mortality at time 0. And well, one more complex thing is I use a base of 1.1. If you can see here, log of 1.1. I didn't use a natural logarithm. The main reason is as follows. Well, we can use natural logarithm for base of 10, and we get exactly the same pattern. But this part, this scale will change. So the question is, why did I use 1.1? By using 1.1, this one change, well, from 0 to 1, this means 10% increase in GDP. So 10% come from this 1.1, this is a 0.1 part. And if we use here, instead of 1.1, if we use 2, the 1 unit change indicate if GDP doubled, what is association? This is going to be the a interpretation of this number itself. And when we use when we take natural logarithm, the 1 unit change is going to be equal to when GDP changes by 2 point, I forgot the E, it was 2.74 something. So which doesn't make up much. That is the reason why I use 1.1. But for graphical analysis, usually it doesn't matter. Not usually, always it doesn't matter which log we use. Okay, because here our objective is to see the association, but I want to make these numbers more meaningful. And well, I said a lot before we look at this plot. But for men and women, we see kind of increasing pattern as GDP per capita changes positively, meaning as GDP increases, it seems that mortality also increases. This is association we see. Next one, this is a similar plot, but the difference is now here, this graph, I looked at the average GDP across these 10 years versus average mortality rate in this period between 2005 and 2015. So this is only, well, this one is as of 2015. Sorry, I made a mistake. This is not 2015, but this should be this 2005. And this is of 1 time point, 2005, and this is the average. So although they are somehow different, but very, very similar in terms of association. And here we look at the longitudinal effect, change versus change in GDP and change in mortality. But when I say change, well, which is given by GDP at time t minus mean of GDP. But again, well, we have upward trend, which is same as the one we saw. And also women has slightly higher increase as compared to men. Do you have any question up to now? No. Then we move on to the regression model. Then, so here you go. It's a little bit busy table, but the top one, these are results we get when we use initial GDP or GDP of 2005 when we partition GDP into cross-sectional and longitudinal component. And the lower table shows a result when we use city mean to partition GDP into cross-sectional and longitudinal for men and for women. And when we include only time, and when we include time plus GDP. Well, first of all, when we compare this one, and this one, and this one. So we are comparing vertically, and they are very similar, according to me. So in our case, it doesn't that matter which one we take, well, initial value of GDP or mean GDP to decompose GDP. Then we are interested in this one, where if the GDP per capita, change in GDP per capita is associated with change in mortality. So for men, 1.1, unfortunately, it means that there is no association. There is no association, and p-value is quite high. And for women, it was 1.03. Well, it means that since 1 unit change means 10% increase in GDP. So 10% increase in GDP was associated with 3% increase in mortality. And it was significant or at alpha level of 0.05. So this is what we observed. And well, afterwards, I was thinking, well, I could finish my session here, or to explain how we can model one predictor into two components, cross-sectional and longitudinal. But for this one, well, when we interpret this one, well, this is what we observed after we adjusted for general trend in mortality. Okay, because time is included in the model. So I wanted to know also, if we do not consider general trend in time, what is the association between GDP and mortality without accounting for general trend in mortality? So I wanted to get GDP only here, but I cannot do using random intercept and slope model, because if we drop here, we are going to drop this term, or this beta coefficient, but as well as we are going to drop random slope for time as well. So if we drop time, we cannot compare with this model because we are including different coefficients, not only time, but also random slope component. So what I did was I fitted the random intercept model. Okay, so in terms of equation, this is the only difference. Here, previously we see beta 1i, meaning this one changes by city, but now I didn't include random slope. So this one is beta 1. But the problem is now, within the city, we have 11 years of records. And by doing this, we are now not accounting for correlation within the city. This is a problem. So, but the good thing is we are applying robust variance estimation, which account for misspecification of variance. So this is my justification. And by using this, we should be able to account for correlation within the city. Not in a perfect manner, but to a certain extent. And then let's look at this one, which is man. And so time, the effect of time, it declined a little bit. And also in terms of significance, it declined. Not declined, it increased. So from significant to non-significant. And when we look at GDP, well, so there was an upward trend, meaning, well, the change in GDP has positive association with mortality. In other words, change in GDP was associated increase in mortality. So this is what we observe when we don't include time. But after we include time, after we adjust for time, it becomes smaller, the effect. Also, and a similar thing was observed in women as well. This is what we observed when we don't include time, but after we include time, it declined. Although in this case, it was still significant. Then we have to think, well, is it a good idea to adjust for time or adjusting time, which is better when we want to assess GDP? So I'm more thinking about, are we, by including time, are we over adjusting or not? I mean, so we have to think, what is the meaning of this? Well, so we accounted for general time trend, and we are looking at the effect of GDP after accounting for general change in mortality. So this is something we have to think, but since this is not the scope of today's presentation, so I do not go much in detail, but this is somehow the complexity we have to think when we do data analysis. And I think this is the end of the regression result. So before we go to summary, I go to summary. So we reviewed how to assess the association between initial predictor value and change in outcome using that interaction model. And also we reviewed how to assess the association between change in predictor and change in outcome. And we also get to know two methods in decomposing or partitioning the predictor into two components, cross-sectional and longitudinal component, or between city and within city components. So this is the end of my presentation, and I wonder if you have any questions. Was it overwhelming? Okay, so it seems not. So if you have any questions, please let me know later. And this is the reference about the decomposition predictor. So if you are interested in which decomposition method is better, you may want to refer to this paper and web, which may be informative for you to decide. And well, this is the end of today's session. And thank you very much all. And also, although I'm going to circulate email, this is the end of this mini start session. So we are not going to meet every month starting from next month. So if there are anything, we may have this session on ad hoc base. But this is the end of this series. And thank you very much all.
Thank you, Goro, for all the sessions.